In case of integrated rate law for the first order reaction, we have a reaction, suppose A gives to product. Now for this reaction we have to derive the integrated rate law. Right? Now firstly we have already seen the differential rate law for any reaction. So rate is equal to minus d upon dt, that is the instantaneous rate law, right? And also we know that rate is equal to k into concentration of a normal rate equation. So as we know, rate as well as rate, so rate is equal to minus d upon dt is equal to rate is equal to k into concentration of a. You can compare this both terms, minus d upon dt is equal to k into concentration of a. So rate is equal to minus d upon dt is equal to k into concentration of a. Okay, now just we have to use this comparing terms for the integration. Now just see, rearranging concentration term on same side. Here we have d into concentration of A as well as k into concentration of A. Now this concentration of A, both concentration terms, if we take at same side, then this, if this dA comes this at denominator, then dt will go here. So minus d upon concentration of A is equal to k into dt. Now just this minus sign will come at this side. You can change the side of sign of right side. You will get this equation, that is d upon dt is equal to minus k into dt. This one is equation number 6.5 in your book textbook. Now we have to integrate this term. So in case of concentration terms, on this side we have concentration. Now while integrating this concentration term, concentration at 0 time and concentration at t time, right? So A0 is the initial concentration at time t0, means initial concentration, and AT is the final concentration at time t, right? Now in case of time also, time will be vary from 0 to t. Okay, on integrating the equation 6.5 that we have this, we have to integrate this equation. So just put this terms in integration. Now see, concentration term is changes from A0 to AT. So A0 is the initial concentration and AT is the final concentration. Just put this integration, dA upon concentration of A is equal to, now the second term is k into dt minus k into dt on integration 0 to t. This is this time term, no? Dt is the time. So time is vary from 0 to t. Now dA upon concentration of A. So just leave it as it is now. Now in case of this integration, minus will be outside, k is the constant, it will be also outside. Then integration of 0 to integration of dt 0 to t, right? Now we have to solve this integration. Okay, so we have equation, that is dA upon concentration of A 0 to t is equal to minus k integration of dt, right? 0 to t. Now while solving the integration of dx upon x, or you can say 1 upon x into dx, the term is log natural x, right? So we have the same d concentration of A upon concentration of A, so you can write log natural A, and limit term is A0 to AT. So just keep it here as it is, A0 to AT. So is equal to minus k as it is. Now in case of this dt, d of x is equal to x, right? D of x is equal to x. So we have this time term, that is dt, so it will be t, and integration limit is 0 to t. Okay, now substituting value of limits. See, while solving this, you have to just do, that is upper limit minus lower limit, upper limit minus lower limit. So log natural AT minus log natural A0, log natural AT minus log natural A0 is equal to minus k as it is, and time t minus t0, so t. Okay, or you can also write by rearranging this equation by using this formula, log natural A minus log natural B is equal to, or you can also write in fraction, that is log natural A upon log natural B. So A minus B, you can also write A divided by B. We have to do the same thing, that is log natural AT minus log natural A0, right? So just write log natural AT divided by log natural A0, log natural AT divided by A0, and minus KT as it is. Now just see, we have to remove this minus sign. Up to this it is clear. Now we have to remove this minus sign. See, while removing this minus sign, you have to just flip the fractions. Means A0 is a denominator, you have to take it on numerator side. So log natural as it is, it was 80 upon A0, so you have to write A0 upon 80. A0 upon 80 is equal to KT. We have removed this minus sign, is equal to KT. Now we have to find a rate constant, right? Rate constant for first order reaction. So for equation of k, that is rate constant, just rearrange this equation. This t on multiplication, it will go in denominator on this side, right? We have to just refer k, so t will be goes in denominator. So k as it is, k is equal to log natural 80 a0 upon 80 as it is, log natural a0 upon 80. This t will be in denominator 1 by t. Okay, now converting, we have this log natural term, right? Now we have to convert for calculation also. We have to convert log natural to log to the base 10. So while converting into log to the base 10, you have to multiply that term by 2.303. So 2.303 into 1 by t into log to the base 10. We have log natural. Now we have log to the base 10 a0 upon 80. Now just while doing multiplication, 2.303 upon into 1 by t, we'll get 2.303 upon t, right? So 2.303 upon t log to the base 10 a0 upon 80 is the value or is the expression for rate constant k for first order reaction. Okay, so this one is an important question. They can ask question on this for 2-3 marks also. Now next, if our reaction condition is in liquid state, okay, then you can say A0 and AT in different terms. So initial concentration of that reactant is considered as A, and after time t, while after doing the reaction at time t, if the concentration of reactant decreases by x, then you can write at time t the concentration of A is decreases and you can say it is A minus x, right? A minus x will be the concentration at time t. So initial concentration was A, and after time it will be A minus x. So you can write this equation, k is equal to 2.303 upon t as it is, log to the base 10 as it is. Now A0 is the initial concentration means A, and after time 80 means it is A minus x. So this equation for if the reaction condition is liquid medium, right? If the reaction taking place in a gaseous medium, then it will be differs by pressure. It will be also in case of pressure, right? The concentration term is in case of liquid, and while doing reaction in gaseous phase, it will be in a pressure. We have already discussed in the last lecture. So if you have any problem about this, you can ask me again. Thank you.